Okay, a regular indefinite integral that we've been doing so far is an antiderivative. It spits out a function. The indefinite integral spits out a function whose derivative is your integrand, the thing you had inside. A definite integral, where we'll have numbers here, is an area. It's a number, and it spits out the area between the curve of this function and the x-axis. And it's defined to be the limit as the number of subintervals in a partition goes to infinity of some Riemann sum. This is equivalent to saying the limit is delta x goes to 0, where the width of our little rectangles in our Riemann sum goes to 0. Provided this limit exists. If this limit over here doesn't exist, if you have some infinite or unmeasurable area, then this definite integral would not exist either. When it does exist, we would say f here is an integrable function, and pretty much anything you can imagine is going to be integrable. It's a lot easier to take the integral of a function than it is its derivative. Like, we have a lot of functions, absolute value of x, you can't take the derivative at 0. Derivative is not defined because of that sharp corner. You can integrate any function that you can write down using elementary functions, you can integrate. Now, all we care about here in this little yellow box is continuous functions can be integrated. It's actually much stronger than that. Any piecewise continuous function can be integrated. So if you can draw a nice pretty graph of something, even if there are jumps and breaks and everything, we can still find the area under the curve. We can still integrate. So the definite integral of this function here means the area between the graph of that curve and the x-axis. And for everything today that we're going to be doing in these videos, we're just going to use geometry to find all of those areas. We'll learn next time, once we learn the fundamental theorem of calculus, how to use antiderivatives and the definite integral to evaluate, and the indefinite integral, the antiderivative, we'll learn how to use that to evaluate these definite integrals. For now, for everything we're doing today, we're just thinking about areas. And we're just going to use geometry because all the shapes we have today are formulas or areas we know the formula for. So let's look at this guy. If I consider that guy there, right there, f of x, square root of 9 minus x minus 3 squared. That is a semicircle of radius 3 centered at 3, 0. That goes up to 3. We could see that if we wrote this as y equals square root of 9 minus x minus 3 squared. If we square both sides, we would get y squared equals this stuff. Move that to the other side, and we have standard form of a circle. You saw this back in pre-calculus. This is a circle centered at the point 3, 0 with radius 3. This notation here says I want the area underneath this curve. So this would be a full circle because we only have the plus there. We don't want the full circle. Down here would be the minus. This would be the plus. See, if we take the square root of both sides, we'd have to put a plus or minus. We only have the top, the plus. This says we want the area between this curve from my starting point, a equals 3, up to my ending point, b equals 6. I want that area right there. But we know how to do that. That's 1/4 of a circle. Because the entire circle would be here. This would be half of a circle. That's 1/4 of them. So this would be 1/4 pi. My radius of my circle is 3 squared. So that's 9 pi over 4 square units. So if these X values were measured in meters, this would be square meters because we're talking about area here. So geometry. Let's stop that one.